I want to introduce you to radiolabeling and how we can use it in colloid science, in particular for colloid tracing. And yeah, this is within the confines of the SURFBIO project. So I thank the EU for financing these activities. And with that, I want to start. So first of all, a few words on why you should use radio tracers. I mean, sounds dangerous if you're not familiar with it. So, but there are several good reasons. I would say the most important ones would be the detectability. You can detect radiation very sensitively over large over several orders of magnitudes. Basically, no other means of detection have these sort of sensitive measures. It comes with a great simplicity. Basically, the detection methods are all what you would call orthogonal to any other methods. So the detection of the radiation is not hindered by anything else in your sample. So as long as this radiation comes out of your sample, you can detect it. And that comes to the third one, the complexity. Basically, what I mean by that is we can ignore complexity. So you have biomaterials, geomaterials that are highly complex in their composition. For any other method, you need to take that into account. You probably need a very complicated sample preparations, while with the radiation detection, you can basically just measure your sample and that's it. And so these are the main reasons basically why you should use radio tracers. And from now on, with that, I will tell you how to use it, where they come from, what they are foremost also, and yeah, how to handle them, and give you an introduction of what you can do with it on the basis of a few examples. So first of all, what are these radionuclides? What are radio tracers? Basically, you might be familiar with this. So these are unstable nuclides or atoms with unstable nuclei that undergo radioactive decay. So the emission of some excess energy is emitted as ionizing radiation that we then want to detect. So these radionuclides or radionuclides are of course defined by their proton number, their neutron number, and their mass number. So with that you can basically define any nuclei that the different elements have, and if they under certain conditions, they are unstable and then undergo this radioactive decay. So this decay happens over time with constant probability, which basically means that the activity, which is the decay events per time, declines in an exponential decay. So you have a half-life. So after this half-life, only half of your original radionuclide is there, and then another half-life, then you go to 1/4 of your original material, and so on. So this is also something that you have to have in mind, of course, when you work with these tracers. There will be a time when they will be gone, and you have to take that into account when you plan your process, your experiments, and of course have to choose a radio tracer that is concerning the half-life that is compatible with the processes that you want to measure. You cannot measure months of release or do a release study over months when your radio tracer has only a half-life of a few hours. So yeah. So these decay modes, or the different radionuclides can have different decay modes. There is a bit more than, or it gets a bit more complicated than what I show here, but I want to focus on those that are relevant for the radio tracing applications. So basically you can have different decay modes depending on the state of the radionuclide. You have nuclides with proton excess that can undergo beta plus decay, which is the emission of a positron, or they can do electron capture. And as you can see, the proton, there's an error. The proton mass the proton number reduces by 1, since 1 proton is basically by these decay forms transformed into a neutron. So that is how the radionuclide gets rid of its proton excess. You have the positron decay. The positron is the antiparticle of an electron, and you have another way to do this is if the so-called electron capture, where the nuclei catches an electron of the outer shell, and using that it can transform an electron in the and proton in the nuclei into a neutron, and therefore reduce its proton excess. This is mostly followed then by X-ray emission, because you have 1 electron missing in the electron shell. Nuclides with neutron excess can undergo a beta minus decay. This you might have heard. This is the emission of an electron, while in the nuclei a neutron transforms into a proton. In general, nuclides with mass excess, so these are large or heavy nuclides down in the periodic table, undergo an alpha decay, where they basically emit a helium nuclei. And the other case would be nuclides with just some energy excess, can undergo the gamma decay, where they just emit the excess energy as a gamma photon. You can see here on the right the so-called chart, radionuclide chart. And basically what you can see here in the middle, the black ones are the stable radionuclides. And then left of them, you have a proton, a neutron excess, and right of it, you have a proton excess. These then are unstable nuclides that undergo these beta decays. While if you go to very large masses, the alpha decay or even the fission comes in. And yeah, so this is the radionuclide charts, where you basically have all the nuclides that are known with their number of neutrons and the number of protons. And here you have a scheme of the different decay forms that can happen, and where the end of this decay ends up. So for our radio tracing, we have to have in mind what are the properties of these decay radiations. You have the alpha radiations, and this is basically a helium nuclei, and this is blockable basically by paper. You can imagine this is not exactly what you want when you wanted to use as a radio tracer. You need the radiation to come out of your sample to measure it. So what you want to focus on when you choose a radio tracer is the beta and the gamma decays. The beta minus decays, so the emission of an electron, is still relatively easily blockable. So for example, by aluminium or some plastic, even a sheet of epoxy resin or something, but it will get out of the sample more easily. And in principle, what you want is some gamma radiation or X-ray radiation coming out of your sample that is not so much affected by the sample itself or by the container that you have it in, so that you can easily detect the radiations. So suitable radio tracer usually undergo beta minus decays or gamma decays. This beta plus decays that I mentioned before with the positron is a special case. We will come back to that, and you will know what is up with that. Okay, so now we know what our radionuclides are, what we can use as a radio tracer. The question would now, how do we get them? So basically, you can isolate the fission products out of the nuclear in a nuclear reactor from the fission material, basically for energy production. You can isolate those products. They will be separated via all sorts of chemical procedures. Basically for any of these radionuclides, you have a special procedures, and basically ion exchange and chromatography is used here for a huge benefit to basically extract different radionuclides for radio tracer applications. Most foremost is the 99 molybdenum that serves as a, later on I will show this as a source of 99 technetium. And the other way to obtain the radio tracers would be to produce them via irradiation. So I can irradiate a nuclide, so it's indicated here by A. I have a projectile which can be anything from a neutron, gamma photon to a proton or alpha particle or deuteron. And by this, I will trigger a nuclear reaction, transform the nuclide here indicated as B, and I have an exit projectile also. So this typically happens also in nuclear reactors, where you use the neutrons as a projectile, or at cyclotrons, so small particle accelerators where you can use protons or deuterons or alpha particles to induce these sort of nuclear reactions. One can calculate the produced tracer activity. So the activity here is of course the decay rate of the nuclide B over the time t. And if you set in the particle flux and the reaction cross sections, which is basically the reaction constant, if you want to liken it to chemical reactions, you get a production curve like this, where you produce, of course, the radionuclide B, and then after some time, you run into a saturation. So this is just, it doesn't make sense because or you run into this saturation because the radionuclide, of course, also decays. And at some point you reach the state where the same amount of produced radionuclide decays as you produce at that moment. So you have the saturation effects. So it doesn't make sense to irradiate longer than 10 half-times, for example. Here in this table, it's just for your information. We don't have to go through that in detail, but what you see is what kind of reaction you can trigger with what kind of energy projectiles. And that then, of course, depends how you run either your nuclear reactor or your cyclotron, which kind of energies you can reach, and then what kind of nuclear reactions you have basically at your disposal to produce radio tracers. Of course, this is now rather theoretical. So I want to basically show you one example of radionuclide production by irradiation that we have established at our cyclotron here at the HZDR. Here you can see our cyclotron. So within these bowls, so to speak, the protons will be irradiated, and then they can be targeted onto or directed onto a target, typically here for a solid state target, or here this is a liquid target. So to induce different nuclear reactions that we then use to produce radionuclides. So I want to just go quickly through the production of zirconium-89. So first of all, we looked at the nuclear reaction that is at our disposal. What you can see here, what we got from literature, is the reaction cross-section of this reaction. So the PN reaction from yttrium-89. Our cyclotron gives us a maximum proton energy of 18 mega electron volt. And then according to this, we have designed this target. Basically, it's just some aluminum casing that is clipped together with an aluminum window. This window reduces the proton energy so that we are here in this green, area indicated by the green bar. And so this is basically what we use, the energy of protons that we use to induce our nuclear reaction in this yttrium foil. So it's a metal foil, and so this gets irradiated, and then afterwards we have to, of course, go through a tracer separation. We have the foil that will get dissolved, and then we use the special ion chromatography resin to isolate our zirconium-89, and that we can then use in our radiolabelling studies. So when you have the need for a radio tracer, first thing is always check which kind of instrument you have, which energies, which nuclear reactions you have to access to, and then develop the target and then the tracer separation. So this goes all into this radiolabeling procedure. Probably you're lucky and somebody else does this for you, and you will then just get the ready radionuclide. Another method to obtain radio tracers would be so-called radionuclide generators. Here I have just an example of the so-called technetium cow. What you do there is basically the technetium-99M, which is a radio tracer that is used for many applications in nuclear medicine. It has a 6-hour half-life. So you cannot transport it anywhere. So what you do is basically you use the 99 molybdenum. This is fixed on a column. This has a higher half-life. You can transport these without it basically being gone after a couple of after 3 days. And then what you can do is you elute the daughter nuclide, the 99 technetium 99M, and it is ready for use in your studies. Yeah, so basically these 3 methods is how radio tracers are produced, how you can obtain them for your studies. And if you are mainly on the so the end of this chain, you basically probably would get these radionuclides ready for use in your application. If you have a nuclear reactor or a cyclotron, you can do these things yourself. Otherwise, quite some radionuclides are also available commercially from nuclear reactors or cyclotrons. So now we have our radio tracer. Now I want to tell you something about the modalities of detection. So I won't go into much details how the detection works within the different instruments. I want to show you some methods of detection and what kind of information they will give you. Here you can, I try to group these in like 4 different types of detection with increasing dimensions basically of information. First one would be just a simple batch quantification. So the detector, whatever it is, indicated in pink, and then your sample. So this would be just a batch vial, and the radiation, if it leaves the sample, as indicated here by these different waves. So you see the lower energy wave might be absorbed in your sample. This is also then, of course, could be a very low energy gamma photon or these particle radiation, so low energy beta, and for sure the alpha particles will get absorbed significantly by your sample, so you cannot easily detect it from outside. But we can also detect. I will come to that shortly. Then you can think of a modality like where you have basically a column, and you have some inline detectors to detect breakthrough curves, or a column scanner, either a detector that moves alongside the column for you to yield a deposition pattern, or several detectors alongside the column. So here you get basically a 1D distribution alongside the column. For the breakthrough curve, a 1D information. The dimension is, of course, time. If we want to go further, we have the autoradiography. What is this called? You can measure the 2D tracer distribution, and using positron emission tomography, for example, we also have the possibility to get 4D spatiotemporal tracer distributions. Yeah, so back to this batch quantification. If we have very low energy radiation, like the ones that wouldn't leave our sample, we have to use these liquid scintillation counting, where we basically have a liquid scintillator, which comes in these batches. You mix, it's basically a couple of organic polyaromatic, polycyclic aromatics, some surfactants, And you can mix that with your sample, shake it, and then the radiation, or you brought basically the detector into your sample. The radiation in your sample will trigger some UV emissions of these liquid scintillation molecules, and they will transform it into UV radiation that can then be detected. Of course, yeah, the sample size is about 1 to 5 milliliters. The advantage of using this is, of course, you can very easily then also detect the low energy radiation, for example, from tritium or carbon-14, which are relatively often used for labeling organics. The disadvantage, of course, is that it is basically a destructive method, because in the end you have your sample mixed with these scintillation cocktail. For some higher energy gamma emitter, you can use the gamma counting, depending on your, or there's a multitude of instruments, of course. This is the one that we have. Here you can measure samples up to 20 milliliters. The advantage is the very high dynamic range from 1 to 100 kilobecquerels, so several orders of magnitude that you can detect. It is automatic, so you don't have to sit there and exchange the samples. Yeah, I usually, if I have very many samples, you can run this instrument overnight or over the weekend. Some disadvantage is maybe the rather low energy resolution. So the gamma photons that are emitted in their energy are specific to the radionuclide. So you can, by that specific radiation, identify a radionuclide if you have a suitable energy resolution of your detector. If you want that, you can use the gamma spectrometry. Typically, this are semiconductor detectors that have a very high energy resolution. So with this, you can identify the radionuclides in your sample. This is, of course, mainly important if you have more than one radionuclide in your sample. And if you do dual labeling studies, that can be very advantageous. This is, of course, the way to go. The disadvantage can be you need to, if you have a very long, very many samples, and you have to manually measure these samples, yeah, that's a bit time consuming for these measurements. The 1D detectors, so the inline detectors and the column scanners, yeah, basically this inline detector does not really have a disadvantage. It's very nice to have to record the breakthrough curve. The sample size, okay, I should have deleted this. There's of course no sample size. You can see here the detector is shielded, and here you can basically run through the liquid that comes out of your column, and then you get a recording of the breakthrough curves through time. The column scanners give you the deposition patterns. What we have available is one that basically moves up and down the sample, or this one where we have a detector array alongside the sample or the column that lets us detect basically individual breakthrough curves. Yeah. And for this 2D tracer distribution that is called autoradiography, what is typically used nowadays are these phosphor storage screens. So these are radiation sensitive crystals that are in a film in these plates, and they store the energy of the radiation, and then you can read it out with these, for example, this biomolecular imager which basically just shoots a laser on every pixel. Then the energy gets released as a light burst. And for that, you can get then the 2D tracer distribution that was imaged on your plate. Yeah, the sample size can be basically as big as as large as your available phosphor screen. So at maximum, we have 20 by 40 centimeters. However, the sample should be very thin and flat, of course. You can see this indicated here. This has a impact on the available resolution. So if you have a thick sample, for example, any activity will basically imprint itself on a larger area, so you get a lower resolution. The same is if the gap between this phosphor screen and the sample is large. Yeah. So also of course, the thickness of the screen itself can be of importance. So that means I cannot tell you the specifics resolution. That depends really on your sample, on the radionuclide that you use, basically on everything. Because you can imagine if you have a radionuclide with a high radiation energy, so something that originates here and it has a long reach, basically could also imprint an image over here. So basically for this method, you want more of these low energy radiation. So these are typically used for beta minus radiation or decays. Yeah. You can then, this is a quantitative method. You can produce these images as here, and you can evaluate them with Fiji, for example, ImageJ, which is a free software to get quantitative data. And this is, for example, different spots of europium sorption that we have quantified on some geometric sample. Yeah, so europium, picomole europium here per square centimeter. Okay, now for this positron emission tomography that gives us this 4D spatiotemporal tracer distribution. Here you can see, first of all, how the instrument looks. You can get an idea about the size of the samples. So usually these instruments are used for animal experiments. So it's made with a rat basically in mind. Yeah, we use it for geomaterials for these sort of columns, and we can fit in 10 by 20 centimeters columns inside there for imaging. The principle of this is a bit different or a bit special. So for positron emitter, you have the unstable parent nucleus, which then emits a positron when it decays. And the positron is, of course, the antiparticle of the electron, and electrons are all around. So it will meet after a very short reach an electron, and it will annihilate with this electron. And this will result in the annihilation radiation. So 2 gamma photons are emitted with the energy of 511 keV, which is equal to the energy of this electron-positron pair. And those go basically anti-parallel to each other. And using these sort of detector ring, which you can also see here, these are these detectors that are indicated. You can basically draw, when you have coincident detection, you can draw a line, and then you know, if you have two decays, then you know where the sample, where the decay happened, so where your tracer was. And due to this traveling time and due to the dimension of these detector crystals that you cannot make extremely small, this method will detect your tracer within a volume of like 1 micro cubic liter. So it has a resolution of about 1 millimeter on a millimeter scale, but within that resolution, it's very accurate due to very accurately detects any changes within these volumes. So what you can do is, of course, some process tomography, and you can combine this with other tomography methods, for example, CT, where you get the geometry, and then with the GeoPet, you can measure basically flow through that geometry, for example. That's what we use it for. And yeah, so we now know what radio tracers are, where we get them from, something about how to detect them. Now we only need to get them into our colloids. So I tried to put the different principles that you can use in these, sort them into these 5 categories. First one would be radiosynthesis, which is basically a synthesis of a colloid or a nanoparticle using radioactive starting material. Yeah, this is straightforward. You do the synthesis and you use the radioactive starting material. This is relatively versatile if you have an easy synthesis route available, and you can add as much radio tracer as you like, basically. So of course you have to think about what, in the end, what do you want to detect? How much of these particles do you still want to see? And you have to add then the radionuclide activity accordingly. Another method that I termed radiochemistry, even though synthesis and chemistry is basically the same, I wanted to distinguish these by the name. So with the radiochemistry, I mean we bind a radio tracer to an existing colloid or particle. And yeah, so here, of course, the yield of the activity, or the specific activity that you can get after this process is dependent on the yield of this chemical reaction. And of course, you have to have in mind that due to this chemical reaction, you could change the properties of your particle. So for any of these methods, basically you have to do a detailed characterization of the properties. You can use different spectroscopies, microscopies in order to see, did you change the properties, and if yes, to what extent, and what are they? Are they still representative of your original material? So if you don't have these radiosynthesis or radiochemistry routes, one easy thing for temperature stable particles would be the indiffusion. It's basically just you give the radionuclide solution on top of your dry particles and you heat them up, and then you have this indiffusion process where the radionuclide will diffuse into the surface defects. And yeah, what you have to have in mind with this, again, if you do this at higher temperatures, do these temperature change your particle or not? We have done this, for example, for cerium dioxide or titanium dioxide. These you can heat to 200 degrees easily without changing the particle properties. However, if you do the same concept with silver particles, you will just melt them down. So that is what you have in mind. Yeah. So if you have access to a nuclear reactor or a cyclotron, then you can go for the activation route. Basically, this is, as I have already talked about these during the radionuclide production via irradiation. Here you basically produce via irradiation your radio tracer in your particles. Also here, you have to check, of course, do you change the particle properties if you take this, if they undergo this experimental procedure. Often it's not so much the radiation that will change your particle properties, but the heat that is generated during this activation. If you have nothing, so no synthesis route, no suitable chemical reaction to bind the radio tracer, no suitable nuclear reaction to activate your sample, you can try this recoil labeling. Basically, here you mix the particle with a lithium salt, and then you irradiate this mixture. And if you irradiate this with protons at the cyclotrons, the lithium will undergo a proton reaction, a nuclear reaction, PN, so proton in, neutron out, will form beryllium. And from this nuclear reaction, there will be a recoil, meaning the beryllium-7 nuclei will basically fly through the sample and will eventually implant itself into a particle, or at least a subset of these produced beryllium will implant itself. So this is something where you can introduce a non-chemically bonded or radio label into the particles. So just to give you a short overview, what we have done so far, established at our place for these different methods. So here you can see we have basically managed to radio label most of the common nanoparticles that are under discussion for environmental impacts and so on, or in applications. For what is mainly important maybe for you is have a look at the half-life, so that you know what kind of tracing experiments or how long you can use them in tracing experiments. And of course, this detection limits. You can see that we can basically detect them in the nanogram per liter range. And to come back on to my first slide with the complexity and simplicity. So we can detect these particles in the nanogram per liter range, basically without any sample preparation and without having to have any preparations, separations, and of our samples. And yeah, so I have not given you very many details about these different routes or how we did this. I now want to basically, because you can imagine you have these methods and you can do everything and nothing with them, basically. So it's basically up to your creativity, how you use radio tracers that you have available and how to implement these methods. So I cannot give you a massive overview about all of what can be done. So I would just want to give you some radio tracer studies, examples, so that you can see how we use these methods and and maybe get inspired about how you can use them. So first of all, what we call the smart radiolabeling of cerium dioxide nanoparticles. We use our cyclotron particle accelerator. And basically with this, we have two routes to go. First, we can produce cerium-139 radiotracer from lanthanum-139, so it's a PN reaction. Of course, everything goes in there. What I told you before, you have to have a look at the reaction cross-section. You have to create a target design, and then you can separate the radionuclide by chromatography. And then we can do a in diffusion labeling. Here you can see with temperature more and more radionuclides that we bring onto our particles will actually stick to the particles. These 99%, this was basically at 300 degrees Celsius. The other way that we can go for the radiolabeling of the cerium dioxide nanoparticles is the activation. This is actually a more complicated step, or from concerning the nuclear reaction, we go from cerium 140 to praseodymium 139. So it's a P2N reaction, actually, which will then decay with very short half-life to cerium 139 again. Again, you have to have a look at the cross-section, and you have to develop a suitable target. Then afterwards, of course, you can have to do a characterization. Have you changed these particles? As we can see here, we haven't. And what we then get is basically cerium 139 labeled cerium dioxide that are for all intents and purposes physically, chemically the same. However, as you can see indicated, the distribution of the radionuclide is quite different in these particles. And if you imagine that we dissolve them, what we can see for the in diffusion route, we get a high radiolabel release upon dissolution because the radiolabel is closer to the surface of the particles. And for the activation route, we get a lower radiolabel release. This we can, of course, use to track dissolution phenomena. And we have done this in the case of plant uptake of these particles. First of all, we did a quantification, of course, so in the roots and in the shoots and the leaves of plants. If dissolution would play a role during this uptake and the translocation, we should see different activities for the different batches of radiolabeled nanoparticles. We don't see them, so we figured this. It's a particle-based uptake. It is localized using autoradiography, so we see them in the edges of the plants where the water flow ends and in the leaf veins. And we can also say something about the fate. If we wait a little bit longer, this distribution changes, and so there we interpret this as a dissolution of the particles in the plants. So what we see is a particulate uptake along the water current, and then with a subsequent dissolution of these particles. And all basically done without any sample preparation, if you don't count the radiolabeling, of course. Yeah. So another example where we took this to another level, we have now our dual radiolabeling of cerium dioxide. It's basically the same concept, but now we use different radio tracers on the same batch of particles. So using a nuclear reactor at the Josef Stefan Institute, actually, we got an activation route, and for our cyclotron, we did this in diffusion route, and then we have the dual labeled nanoparticles, so cerium 141 and cerium 139, which are not differently distributed in these particles. And then we can do the same but this, as before with the plants, but this time with the with one particle batch that has both labels that are released to 2 different degrees upon dissolution. And we have used this to track particle uptake in freshwater shrimps. So you have the dual labeled nanoparticles. We check them by UV-vis transmission electron microscopy to see if we induced any changes, and then we fed them basically to some freshwater shrimps. And what we saw then upon monitoring the remaining activity in the shrimps over a month, we saw the elimination of the different radionuclides from the shrimps. And as you can see here, after day 20, basically the radionuclide ratio jumps by an order of magnitude, and serum 139 does not get any more eliminated from the shrimp, while the serum 141 still goes. So we have an accumulation in the end of the serum 139 that remains in the shrimp. And from autoradiography, we can localize these shrimp, this activity here in the lower thorax of the shrimp, which is, of course, the hepatopancreas of the shrimp, which deals with the heavy metal elimination, basically. So yeah, so this within one experiment on here live shrimps, we could show the dissolution-based uptake and accumulation. Yeah, another example here, just shortly, because I want to mention any of the different techniques one time. So we have the recoil labeling that we used for multi-wall carbon nanotubes. They had to be multi-wall because the beryllium has to stick in between the layers, of course. So it has to have something to stick in between, so it doesn't work with single walls. And the other thing that we radiolabeled for this experiment was quantum dots, where we had a 2-step synthesis to yield cadmium selenide capped with zinc sulfide. And here we could radiolabel the core with the selenium 75 and the shell with zinc 65. Yeah, and these particles we used to look at the fate of nanoparticles in a model wastewater treatment plant, which you can see here in the upper left. First of all, we could, by sampling, we could show that the association of the nanoparticles with the sludge in the, so this is the organic waste and the microorganisms within the, this happens within minutes. And then the elimination of the nanoparticles from the plant will basically go with the sludge according to the preset sludge age. It's basically how much sludge you take out of the wastewater treatment plant controls how fast they are eliminated. And then, of course, at the end of our experiment, we could very much quantify the distribution of the nanoparticles. So at the end, 90% of the nanoparticles have left the wastewater treatment plant with the sludge, 9% remained, and 1% got eliminated with the water. And from this water, we sampled and filtered, and so we could say that just the free nanoparticles were just 0.1%, and the others were sludge associated. So as I showed you, we did a dual labeling for these quantum dots that, of course, gave us a bit more information. It's once again one of these dissolution mechanisms. And what you can see here is then the selenium 75 to zinc 65 ratio. And in the sludge, it grows with time, while in the water, it decreases. So from this, we can figure that there is a slow dissolution of these quantum dots in the wastewater treatment plant.
The last example, which I just want to, it's basically example for the this radiochemistry. We have a graphite. It's not the most sophisticated chemistry. It's basically just letting a solution of F18 salt dry on these particles, and then we track these in the deposition and mobilization of this graphite dust in a pebble bed reactor. So using a positron emission tomography, here you can see our positron emission tomography. These were the pebbles, and basically in a circular flow, these particles were run through these pebble bed. And here you can see then the evolution over time, how they deposit on the particles, on these pebbles, basically, and how they are also, again, purged from the pebbles. Yeah, basically what we can see was a particle deposition at lower flow rates. And then if you suddenly increase the flow speed, then you get a particle remobilization, not total remobilization. And of course, these sort of studies were done with respect to nuclear safety, because one new type of reactor could be these sort of pebble bed reactors, where you then would have highly activated graphite dust within that, in case of emergency, could undergo these pressure differences, and you want to know when these particles will be deposited or remobilized. Okay, so the last few words I want to give you after these examples, just a few words on the radiation safety. How can you handle the radionuclides and radio tracers? Basically, you have to follow 5 rules, and that should be: increase the distance, decrease the handling time, minimize the activity. So you should only use as high as activity as you actually need. You should increase the shielding. And of course, you should prevent incorporation of the radionuclides. And yeah, concerning the shielding, we have already seen this before. Gamma or alpha radiation is blocked by paper. So for this, the alpha decays or alpha emitters are handled in glove box typically. Beta radiation will be blocked by aluminum. You typically use these sort of plastic shieldings there. And for the gamma radiation, you need these lead bricks, or if you work with very high activities, you have these hot cells with lead shielded hot cells. And yeah, for transporting your samples, you have these lead containers. And yeah, but basically handling is, yeah, like normal chemistry behind a lead wall, like this. What you might see in a controlled zone are these governmental dosimeters. So your dose will get checked. You have the electronic dosimeters. These are the things that beep when you get high activities, because the governmental dosimeter, they will be read out every 3 months, at least in Germany. But it's not relevant for you if after 3 months somebody tells you you got a high dose 3 months ago. So for this are the electronic dosimeters. And then what you will usually find in these labs is a dose rate meters or surface contamination monitors. And of course, at the entrance, mostly this hand-foot monitor to check for contamination. And yeah. And I want to basically close with the theoretical risks to have a look at this, so that you know what you're getting into. So this is how radiation safety is, or how the legal limits are basically determined with this linear dose risk extrapolation model. So you have 10 sieverts. So that would be, sievert is a dose rate. So it's basically joule per kilogram. So 10 sieverts.
or energy deposition per mass, and 10 sieverts per one person is basically the lethal dose. So from this 10 sieverts to one person equals 1 death. From this, you now go linearly down, you extrapolate this. So 1 sievert on 10 persons, one of them will die, and 0.1 sievert on 100 persons, again, one will die. In this range is, for example, in Germany, the legal limit in case of catastrophe. So for the fireman, if there would be a nuclear emergency, basically. And then you have the 10 millisieverts on 1,000 persons, 1 death. This is basically something the legal, where in this range is the legal limit for radiation exposed workers of 20 millisieverts per year. And then you have the 1 millisievert per 10,000 persons, 1 death. This is the legal limit for the general population, and that's also equal basically to the normal background radiation. So now I don't want to close with all this death, or at least not like this. So let's do this calculation for alcohol, so that you get an impression on what this means. So if you have 1 per mil blood alcohol, 1 person is 1 death. So 0.4 per mil, 10 persons, again, 1 death. And then we are at the case of catastrophe. In case of radiation, the 0.04 per mil at 100 persons, 1 death. So that's about 1 glass of orange juice. Yeah. So this is just to show you that we can safely handle radio tracers. It's not something that you have to be afraid of. And yeah, I wrote it in bold. These are the theoretical risks. These assumptions, we know that they are not true. They are a bit exaggerated. Of course, you want that to be safe, and yeah, but you also don't need to be afraid about handling these sort of materials. And just to give you an impression, I usually don't get over 1 microsievert per day, which is basically close to the background when I work with the right shielding in our controlled area. So 1 microsievert per day means I can do these 20,000 times or days per year to reach the legal limit. And yeah, so with that, I want to thank you for your attention. It took a bit longer than I wanted. Sorry for that. I hope I could show you how to or introduce you to the radio tracer and convince you that it's for good benefit to use them and that you can safely use them. And if you have any questions, of course, please don't hesitate to ask or to contact me also for this. So thank you very much for your attention.
Thank you, Stefan.